Flautner, the next speaker, got his PhD at Michigan. Krisztian is as I already said, CTO at ARM, a very influential guy in spite of his age as well, and very hard to schedule. And we tried to get him here to speak at the Multicore Day before, but it's been hard to make all the dates work out. So I'm extra happy to have you here today. Thank you.
Thank you. How do I put this on, actually? Oh, like that. All right.
Good.
By the way, I hate to disappoint. I'm not actually the CTO. I just work for him. So I'm the VP for the research and development, but it's the same group. And the title of the talk is State of the Future. It's a generic talk I keep on revising every year, and this year I decided to put some different material in it. But it's just generally about what's going on in the industry and in some of the research areas we care about. And to set you the context, some of it is a bit like gazing into a crystal ball, and this kind of contrasts with what Alan Kay said about what to do about the future. But you can make the observation that those two things go hand in hand. You have to set some goals, and then you try to kind of work towards them. And a lot of it does come down to crystal ball gazing and what's happening in your mind. If I go back, I guess one of the nice things about our industry is that there's actually a lot to be known in advance. You can kind of look out 10 years, and it's not as difficult as it might be in some other fields. And sometimes it's surprising. I mean, I remember in 2007, this is where I was trying to explain in an old version of this talk that actually the world changed a lot from when people grew up in the 90s and they set their expectations on how Moore's law actually worked. And in this picture, you can see that actually back in the 90s, going from 180 to 130, you actually went up 30% in performance, and at the same time, at that performance level, you were only using half the power as the previous generation. And even, different, but even bigger gains when they went from 130 to 90. This was happening because this is back in the days when things actually scaled. When you went around 65, the things stopped, and they started slowing down. You were still getting improvements in the headline metrics of these processes. Things were actually getting a little bit faster, but you're not getting the equivalent power reduction. And so there was a shift, and as far as I could tell, people didn't really realize that there was a shift, because it just happened that bits of companies were working much, much harder to keep up the illusion. People were designing things, they started caring about implementation, and they started caring about lots of microarchitectural details that you could forget about and system-level things. But it's worth noting that this is still the world, and when I say that you can gaze in a crystal ball and predict the future, if you understand a little bit about the underlying trends on the transistors, you can kind of sketch things out about 10, 12 years. Not exactly accurately, but at least broadly the trends you can kind of see. So, people had a gut feeling back in the in the early 2000s that was based on the 90s, and I think still a lot of people think that is actually how the world works. So I wanted to say a few words about actually what's going on with the process technology that is underpinning our futures. If you look at technology scaling back in the good days, you heard a lot about how difficult it was, but actually, in retrospect, it was the golden era. Things were easy. Only a few things changed every few years. And this is when, if you're now looking kind of, and you could actually look at some of these high-level metrics, CV per I, power is CV squared F, and areas related to the pitch, and do some predictions going forward. Then came double patterning, and now FinFETs are being deployed, and the question is, can you actually use that to predict the future? And are you going to kind of predict the future with a line that way or a much sharper line going up? I'll argue that this is actually what's happening now with silicon technology, and if you kind of look 10 years out, there's a lot of complexity happening. Now, people debate whether Moore's law is going to end or not, and it's not the relevant question. It's just who will be able to afford it. And the progress has been tremendous. And if you kind of look back, at supercomputing, this is a trend line you could see. Then servers came around and they were kind of on this type of a performance trend, and this is mobile. And this is the performance trend that they're on right now. This is a logarithmic scale and years. And so your supercomputer in your huge military installation is now in your pocket. Well, I guess in a large pocket, an iPad too. But that's the same processor that was in the iPhone as well, about 20 years later. And you can see the slope that these things are on. Now, if you believe that this won't do this, then you can see that they are kind of on an intersection path. And so you will have a supercomputer in your pocket, and you may have 2 suitcases to have a nuclear reactor to go with it. At any rate, so back to that curve. You can actually predict a lot going forward, I mentioned, and this is a prediction of actually how the underlying silicon technology will pan out. You notice how many colorful blobs I have on the right, and this is roughly what people are proposing for these various technology nodes going forward. So notice that you had innovation. The foundries used to introduce one new bit of technology every 2-4 years, copper, and they make a big noise about them. Every generation here, there are multiple things moving to get to this nirvana of whatever, 3 nanometer in the past. So if you actually read the papers in these areas, and I don't, I have some people in my group that do, that understand devices, tell me that people actually, there are devices you can build at 3 nanometer, and people understand the physics behind them. All these technologies are on paper and probably implementable down in the future. So, and this is our kind of their best guess about how this could pan out based on some industry knowledge. You hear a lot about the device part of it. So these are the transistors, the end of CMOS, FinFETs are now happening, and then there are all sorts of different things that are now going. Now, the interesting thing to note, FinFET's actually going to run out of steam fairly quickly. It's 2 generations of process technology. After that, there's going to be all sorts of esoteric things, eventually ending up with spintronics on the right, if we ever get that far. Now, I'm pretty sure somebody will get that far, but is it going to be $1 billion per tape out, or is it going to be, 100 million? That's actually the interesting question. And these devices exist. If you're in device physics and low-level transistors, there are conference papers. There's about 10 years until a technology goes from a conference paper to reality. So you can read about the technologies that we're going to be using 10 years from now today, if you deeply care about it. FinFETs, as I mentioned, probably about 2 node generations worth of life left in them. After that, they kind of go out of kilter with the rest of the concerns around them. A lot happening on how you actually pattern these devices. If you track the industry, EUV has been about to be deployed for the last 15 years. I heard about EUV, extreme ultraviolet, when I was in grad school in the mid-90s, and it was around the corner then. It's still around the corner. And it looks like if it ever shows up, it's only going to last for a generation. After that, it doesn't actually solve the problems anymore, and they're going to have to do something else. Now, they might continue using it, but they might then use double patterning, triple patterning on top of EUV. Nothing is in nirvana anymore. There isn't just one technology that gets introduced and that solves all the problems. These are all kind of stopgaps if we want to deliver this kind of relentless rat race towards the next node and make things smaller and hopefully better in some way. Because of this landscape, and because you can actually kind of figure out where the world is heading, even if you're not exactly where it's going to be, we can actually kind of come up with models of the worlds on those tables. And a couple of years ago, we started this project in R&D because it was a good way of actually getting prepared for this future. And we started developing something called the predictive PDK. And it's quite interesting. We take a lot of information from research papers, we take information from our partners, and we cook up models. And then we look at how our IP performs. Now, to do this, we had to do a whole bunch of predictive things like SPICE models, libraries. We can generate these, layouts, integrate a very large system that you would actually use to tape out a processor today in a real node. But we can do this for all these nodes that people are just dreaming up today. And So, you know, we started this, now we have some models of 10 nanometer. I mean, people have 10 nanometer models in foundries, but what they don't have is actually kind of the higher level know-how about how to pull these together and build larger systems. Now, a larger system in this case is a tiny M3 processor, 43,000 gates. But in the early phase of a process development, actually people worry about the transistors and maybe 2 wires. And with this technology, we can actually worry about, you know, building something that potentially can work. And what do we think about 10 nanometer today? We think that actually, yeah, it is going to be smaller, and it's going to give you some efficiency and or frequency. And like in most technologies, the exactly where you actually choose to develop that piece of IP can vary significantly. So this is kind of a sweep. This is power versus frequency, depending on the type of tape out you do. And we've done these with information from papers and information from foundries about a process that doesn't exist. It will be interesting to see what it'll look like in real life. Now, we've also done these for our dreamt up 7 nanometer nodes and 4, but I don't yet have the graphs for those. I think they'll be much more interesting once we move from an M3 to something much, much larger. So you can do this today, and you can probably actually simulate a processor implemented on that process technology 10 years out today. Question mark about how accurate it's going to be, but you're probably going to capture some of the trends that will then impact the microarchitecture. We started publishing some papers about this, but the caveat is that actually right now we're at the microcontroller level, no memories in this, and the results actually change quite a bit as you start pushing the pushing the size. One thing in particular that's happening in these process nodes is that our computer architects have been talking about wire resistance becoming a problem. Now it is actually going to be a problem in the next decade, because there's very little you can do material-wise to make a wire less resistant, and that's actually probably going to show up at some point. Interesting thing, again, when I look back at my graduate school days, wire resistance was seen as a problem 20 years before it was actually going to be, because people anticipated, but the timing sometimes on these exponentials and also with innovation is difficult to get right. Anyway, if you're interested in some of these models, we have published some of them. Now, we've only published the things that are built on ITRS roadmap data. ITRS is not exactly in sync with reality, but it's the best data that we have publicly available. And I guess the bit that we have actually added to it is we've pulled together a lot of the detail into these models so that you can actually reason about higher level structures. And for a lot of people, reading the ITRS is actually, well, even, for most people, I think reading the ITRS is a chore, and this one actually gives you a model that you can plug into other simulation environments to work with. So I spent some time now talking about the leading edge of process node development in silicon and how important it is to actually predict the future. But I think another part of this future that actually there are always parallel trends. And it isn't just about silicon and how the very expensive things evolve. If you kind of look at technologies that have evolved at a fast pace over the last few years, one of them is display technology, so TFTs and things like that. And it is quite interesting because they're cheap. They're disposable, and actually TFTs, they're much lower than CMOS. They're transparent. Some of the processing requirements are actually much easier than CMOS, and they could be environmentally friendly. And if you project some of these logarithmic trend lines, if you look at TFTs here, and if you look at conventional NMOS and PMOS, they're also on some sort of a intersection line. So process technology used for processors and display technology will overlap at some point, or at least get very close. And I think one of the interesting things about that is that, well, is display technology going to lead to something that actually is a useful implementation technology for other type of processors? Now, some people, this is plasticky stuff, and why is it interesting? Well, CMOS is about $40,000 per square meter, and this is about $10 per square meter. It's all about cost. And what kind of little computers could we build out of these technologies, and when is interesting. I think small microcontrol level things are currently on the tens of kilohertz level speed that you can get out of some of these processes, but in a few years, they're going to be around the magical 1 megahertz level, and at that point, you can do something interesting. I think a lot of us remember 1 megahertz computers and how the wonderful things they could do for you. The interesting thing about these other areas that at least I, as a computer architect, don't think about much is things like printers and the nozzles, the jets that the people engineer, and they do that. They actually are in exponentials, and the droplet size and feature size has been shrinking rapidly, and actually the throughput of these devices have been going up a lot, and and at some point this is actually going to enable some sort of disruption to how we think about manufacturing computer circuits as well. Now, the predictions I showed you on the previous slides were around an M3, and I made the point that, well, M3 is not a large processor. It's also not a full system. And a lot of our understanding about trying to understand this future, it has been around building larger systems and actually understanding how you partition systems in a way. One of the tools that we've put a lot of our own effort behind is the Gem5 simulation infrastructure. It's a publicly available open simulation infrastructure. If you're not familiar with it, check out the website, gem5.org. We actually routinely release back models that we build, and our strategy there is to actually enable the broader ecosystem to actually standardize on some set of models and tools and plug them together. There's quite a bit of activity in ARM actually, pushing things into this. And if you're interested in modeling large systems, there's quite a bit that actually is out there. ARM v7, very soon the version 8 microarchitecture is there. There are different models of different fidelity, lots of kind of enabling network models, peripherals, etc. And we use that and lots of images to then try to do large-scale workload simulation. The problem with some of these workloads is actually, while we would love to release them openly, because of some of the open source licenses, that's not actually feasible. So we tell people recipes about how they can build their own image. But often we can't actually put the image ourselves on the website for all sorts of legal reasons. It's a bit of a bummer. In one of the developments in this recently was the power estimation framework. The more you do simulation, the more you realize that actually there are a bunch of questions you can't actually answer using a simulator, and some of them are fairly important and not that difficult to do. It's just, but they require some fundamental re-engineering and rethinking about what it's about. And we decided putting a power estimation framework in there, and we started at the system level. So this is not necessarily about accounting for power at the instruction level. This is about, well, what happens when an operating system is actually controlling the power features on an SoC? And the other question is actually, how can you make predictions about how that changes if you reconfigure the system resources? Power modeling, I think, is one of these areas that it's extremely difficult for people to actually do at a simulation level, because the usual pushback is that well, you're not actually going to know how much power you're using until you build the system, because so much of it depends on the routing on the specific chip. And I think that's all very true, but nonetheless, people need some sort of a handle on actually reasoning about this at a higher level, because we don't have the luxury about taping chips out just because we want to know power. We have a prototype working in this, and actually you can find this in the Gem5 repository as well. And there's much more that's happening down the line. You can read the paper in Mascot 2013 if you're interested in actually what this does and some of the thoughts about power modeling in Gem5. Now, why are we doing simulation or system level simulation? I think most people do it for the workloads. We do that as well. If you want to build the right systems, you need to understand something about the workloads people are expected to run on them, and you cannot do these anymore at the core level. The other kind of more forward-looking area is actually what we're trying to understand is what the role of heterogeneity is in these systems. And if you've seen some marketing slides from ARM recently, we've been talking about big little processing. Big little was just how we refer to this technology, basically architecturally similar, microarchitecturally different cores. Architecturally the same, microarchitecturally different cores. And one designed for high throughput, that's the big core, and little one is designed to be very efficient. The reason why we got into this was because we made the observation that a lot of our partners actually really are looking for things that are efficient most of the time, but occasionally they can deliver the oomph for their workload that they needed. And could we help them do that with some architectural ways? There are also implementation-based alternatives to this. One of them is voltage scaling and things that you can do, adaptive body biasing. Those are all techniques that people deploy, but there are also techniques that have a limit. When you actually synthesize a design to a particular operating point, you actually can impact the efficiency of that design significantly. Think about it this way. If you take a large core and then you want to get every last ounce of performance out of it, you're going to be synthesizing big drivers, large buffers, and cranking up the frequency. That core will be wasting power even if you voltage scale it down. It'll be less efficient than a core designed for half that frequency to begin with. There, the buffers themselves would be smaller, and so on and so forth. So one of the efficiency plays here is that actually by having two different style of cores optimized at two different design points, you can actually get the implementation engineers to give you an extra degree of efficiency above and beyond voltage scaling. In reality, this can be used in multiple ways. One of them is in combination with voltage scaling and frequency scaling, or you can actually just use it to replace voltage scaling. Not everybody's system is designed equally well for those type of implementation techniques. And there's quite a bit of difference between what our partners do with the same underlying components. The thing what we'd like to do from a research point of view is to actually understand better when we can use the big or the little core, and even variants of those bigs and variants of those little cores on different workloads. So should we be moving tasks between these cores during the lifetime of that task? Should we be statically allocating tasks in different tasks to different cores? What is the right way to handle this? So I guess I've already explained why big little, but it's for efficiency. And at the end of the day, you can gain a lot. So on some of these workloads that people run, you can get significant improvements and significant differences in speed and efficiency when you run them on the different cores. Today, it's enabled by two different kinds of techniques. One of them is you can think of as a virtualization-based technique that tries to migrate a task. If it's a task that requires a lot of performance, it's a web browser, it runs on the big core. If it's something MP3, it runs on the small core. That's kind of the starting point. That is required to make this an interesting proposition. And at the end of the day, the expectation is that this will improve battery life significantly. We're also working on something called Big Little MP, where you try to do the same type of migration decision in the scheduler itself. And this is actually based on heuristics that people develop and watching counters and so on. And that might actually make it into the next generation of the big little systems as well. There's also the option of not actually turning off the small cores and the big ones, but actually using them together. Again, that depends on exactly which application domain people are going after and actually how much throughput they require. They're all possible. I'm not actually, we had a discussion last night over dinner. I'm not actually sure anybody knows what the bestest heuristic is to actually drive this type of MP scheduling, but there's some good enough type of heuristics that people have already come up with in that context. But given this model that you're going to have different cores, small ones, big ones, maybe differently tuned ones, how do you know what is the right configuration for your SoC? Because on some level, heterogeneity is a problem because it introduces an extra dimension that somebody somewhere has to deal with. And what we've been trying to get a handle on is actually the set of workloads and what mix of cores and resources they could actually benefit from. So we've been doing quite a bit of principal component analysis. What are the parameters that we actually care about? There are lots of benchmarks. how do you deal with variance? You know, where do you bias things? How do you actually deal with bias in the data? And can you actually group different workloads in kind of different clusters, like over there? Or are these workloads overlapping in many different ways? So what we've been trying to do is to focus on the internal structure and how the variance comes about. So if you look at some workloads here on this fairly busy graph, you can kind of see clusters in them. There are a set of workloads here, and there's a set of here. You know, the green one's a bit more over the place, and then you see a whole bunch of them. These are the spec workloads on the bottom. So which one is the representative workload, and which one should you be designing your course for, is a question one can ask. If you look at this particular, and then furthermore, if you look at a single benchmark, do you look at the average, or do you look at different phases of that benchmark? So here's one of them. This is the Andy bench, which is, I don't know exactly, it's a benchmark, but it has two different phases that look very different, have different characteristics. It clusters in two different areas. So then do you now design a core for the benchmark, or do you design a core for a type of a phase? And our methodology has been so far to kind of explore both. You know, look at phases, look at overall applications, and then try to figure out how we could best combine them into an efficient system. So our objective is to find the best heterogeneous system for a set of workloads. We look at a lot of workload phases, and then we want to tweak the hardware parameters to make sure that these things run very efficiently. This is, if you kind of contrast this with Jason's approach to how to schedule things on a very large cluster, we're trying to now to build the right component for those right type of workloads at a much lower level. It's also dynamic in the sense that somewhere will have to decide which phase should run on which core. So in many ways, it's complementary, but as far as it will probably add an extra layer of complexity in the decision making. So if we now plot a whole bunch of workload phases against the number of parameters in the architecture that we can tweak, you get this type of a heat map that you see here. And what we were really trying to figure out is that how sensitive is performance to some of these low-level microarchitectural parameters. And does it actually improve performance, or does it actually reduce performance for that phase? So it's not really worth looking at all the parameters here. It's just that, you know, this heat map is not consistent. You see some lines that seem to be more important than others. You know, some of them here don't seem to matter as much as the red ones. So there are certainly things that kind of align over the phases as being more important than not. But then when you look at a large number of applications, you know, this map can be, again, quite different. So the other problem is actually what constitutes a phase. And there are different partitioning ways of actually figuring out where these fall. And this is just one type of partitioning that you could do on this particular set of the workload phases. If you then look at a whole bunch of workloads all together, you can get a map like this. You know, here we care about instruction mix per the misses in the cache versus the CPI and data misses, and you can see that these there are some clusters in it, but some of the workloads in this particular example are just, you know, off by themselves. And you know, if this were a very important application, it might be, then you might actually end up designing a whole different core than for some of the other applications. And I think the reality is this: things are actually quite different, and if you care a lot about them, you're going to have to do something, you know, to cater to them. One size really does not fit all, and in the workloads we've been looking at, there's quite a bit of divergence, and the art is going to be in actually picking the right cut between them to cater to the needs of the people that actually run those workloads. So here's another view of this heat map. You know, if you kind of look at the Gem 5 workload, which is actually the simulator itself, you know, data cache, But it's okay. It's fine there. But data cache matters a lot. Memcached, obviously, it has all sorts of problems with. Is that the instruction cache? I guess. So my point here, without the detail, is actually that these workloads look different. And if you talk about benchmarking, even for something like a class of server applications, you're going to actually find quite a bit of difference. So if you look at Memcached, one of the things we actually found out is that the biggest bottleneck there has to do with the network interface, and that that the iCache matters a lot. And look at the scaling impact of two different enterprise class, consumer class. So this is what you would find in a gigabit Ethernet, Linksys box in your home. And if you're lucky, this is what you have in a cell phone. Often in a cell phone, this would be on the other end of a USB connection, so it's even worse than that. But this is what you would find if you buy a very high-end NIC from an enterprise class NIC provider. And the performance has nothing to do with the processor at that stage. It has to do with the integration of that system and whether they design the right features into that network card that then allows the processor to do parallel execution on those things. And then here you can actually see that L1 actually matters a lot, and processing is not that big an issue. Now, if you're somebody like Facebook who is doing a lot of memory, Memcached type application, this can be interesting. It means that actually you should be designing your service very differently, de-emphasize the processor, and overemphasize the NICs, and put lots of RAM in there, that kind of stuff. Now, the last sort of thing I wanted to talk about in the system context is related to memory. One of the things we actually often forget about is that the system does not really end at the chip boundary. Now, I know data warehouse class people don't forget this, but when you talk to silicon providers, they often forget this because they're selling chips. That's the most important thing. It's somebody else's problem to hook these chips together into a system that works very well. Now, one thing that almost everybody has to deal with is the DRAM and the DRAM performance. And one of the problems there is that DRAM is on a scaling path that is actually delivering density scaling. But if you kind of look at forward projections, they're giving up on some of the key parameters that actually allow people to design balanced systems. So memory is key, and lots of cores are competing for the same set of resources. And we're actually spending a lot of energy in DRAM. So if you look at the power budget of high-end supercomputers, they're often not dominated by the processor, they're dominated by DRAM. And even a small core, at the power budgets today, DRAM is actually taking often 20%, 30% of the overall budget that you account for workload, and I think that is likely to go up as people are pushing the bandwidth requirements into them. So, from a system design perspective, heterogeneity is one of them, but actually it might also end up being heterogeneity of the memories that you have and the hierarchies that you have to support them. That just complicates things even further. And the other problem is that, it's from a marketing point of view. Now we are at the 28p cell phone screen. Marketing will put a 4K, screen into the cell phone very soon. So the bandwidth requirements and the compute requirements related to that bandwidth are just going through the roof. And the question is, how do you deliver them? So on this particular picture is just some of the DRAM-related standards that are being pushed out. And just like you saw with the process technology, there is this kind of a knee here as well. And this knee is there for commercial reasons because of what I mentioned, that people are actually hungry for these bandwidth, and these are the solutions that they have on the table, and they have a roadmap to deliver them because people have to deliver them. So it's an exponential path. And look at these are different people's roadmaps, and they all kind of align on that, mostly because they kind of are on the same committee in JEDEC, so they kind of agree on the big picture. The interesting thing is that when you look at the detail, it's not actually as simple as saying that, well, LPDDR4 is going to solve the problem, or WIDE-IO2 is going to solve the problem. There are all these different standards, interfaces, different ways of coupling DRAM, but actually there are many more problems that you have to solve to actually realize the benefits of that scaling. So people designed to a bandwidth point, and we just did a little bit of exercise about, well, you know, this is the roadmap if you look at the memory vendors, you know, delivering exponential bandwidth. This is roughly what a processor can actually use, because 64-line cache size. This is kind of 128 if you made caches bigger or you were smarter about prefetching and things like that. So they're spending a lot of power and energy on actually delivering bandwidth, and actually the systems that end up using these DRAMs often cannot exploit them. Now, it's not always, because there are different style of architectures. You know, you can actually aggregate some of these lines together, but if you actually care about you know, the general purpose compute, often that's a very hard thing to do. So the DRAM technology is fundamentally mismatched for some of the general purpose compute style requirements, and the question is, what can we do about it? There have been a lot of proposals, and on solving these with different styles of accessing DRAM, different, you know, wide I/O is a much more tightly coupled DRAM die when you have lots of pins going through with through-silicon vias potentially into the DRAM, so you have lots of bandwidth, lots of pins, very tightly coupled. LPDDR is more conventional, and then there's evolutions of that. But even within that, you then have a million little configurations that you can choose from, and the question is, which one do you actually use in your system? And that is also as big a problem as figuring out which type of core and how many of them to use. These things vary a lot, and you have to do a lot of simulation to actually get to a reasonable match. So how do you evaluate them? It's tight. You know, there's a very tight interaction between the DRAM and the CPUs and GPUs. And actually, the reality is that people often ignore the GPU traffic, or there are different teams worrying about them in isolation. So that's actually one of the first order problems to solve here, which is, you know, take a look at the full system performance from a memory reference point of view, not just the subsystem that you care about or design teams. And actually, the right configuration of DRAM may be different if you're GPU dominated versus CPU dominated. We have actually, into Gen 5, we have added a configurable DRAM controller where you can play with a lot of these parameters, and we're actually trying to figure out the right answers ourselves. There is no golden answer to this. There's only a good compromise in every one of these. The other thing that actually is interesting is that if you kind of look at a couple of benchmarks, they actually look quite a bit different. And depending on which configuration you end up, you can have very large differences on bandwidth, delivered bandwidth for each workload. So in the particular example here, we have the green bar, which is an ideal 12.8, I guess, is a gigabyte per second setup, which means that it has a fixed latency, but automagically it can make the right trade-off between latency, between the bandwidth for a given rate. And it can do it faster or slower, but on average it'll be the 50 nanosecond. And this one, the orange one next to it, is actually something that people know how to build. It's a particular configuration of LPDDR. And notice that they actually have the same net effect on performance. One of them requires twice the bandwidth. And the buildable one is the one that actually requires that bandwidth. And the question is, how do you come up with the right knobs and the right settings so that you minimize the impact and minimize the requirements? The problem with counting on over-speccing the system, like doubling the bandwidth for a given performance level, is just simply you're going to be wasting a lot of power, and you're going to be using more expensive chips than you necessarily need to. I think the net result is that there is a bit of an orthodoxy in the industry even about GPUs and throughput compute things, in that latency doesn't matter. Well, when it comes to DRAM, it does. And yes, people do design DRAM for bandwidth, but actually they ought to think about what they could do for latency reduction as well. One of the interesting things on the horizon is something called the hybrid memory cube. There's a consortium forming around this. Various memory makers are in there. We are in it. And this is all about rethinking about how you actually get to the DRAM and the memory side of the compute. There's a working version of this, so this is not just pipe dreams. There's at least Micron has built the prototype. It's very expensive. It's probably 100 times more expensive than what you'd like to pay for DRAM. but it's really a, they're proving a principle here, which is that you can build a DRAM subsystem in a 3D way and actually couple it to some compute so that you don't have to expose the low-level details over an interface. If some of you are familiar with the JEDEC standard for getting a DRAM, it's kind of a standard that specifies all sorts of timing, temperature dependence. It's not something that you can just use in an abstract way. You really have to design both the DRAM and then the controller to tune to it to be able to work. And what we've been really interested in here is actually, could we have a bit of a separation of concern? I'd like to have the concern of dealing with memory. I don't really want to know about how they deliver what I need. And the DRAM makers should be able to put this detail into their own controller on the 3D stack, and perhaps that will make system design easier. So the current one is actually 160 gigabyte per second. It's a fairly small one, but it's 1 gigabyte. But the bandwidth they're delivering is much larger than what conventional DRAM can do today. I think this will become interesting much more as they actually start building these other cost-effective points. Today, I think some of these may make it into some prototype supercomputers or maybe some military applications as usual, but that's about it. Most people won't be able to afford them. So it's hard enough to actually, we all need DRAM, but actually they're also on a trend to really blowing the power budget. So part of the reason they're doing that is because of the interface standard. Things are over-spec'd so that there can be multiple suppliers for DRAM, and there could be much better tuning on the die itself. And at some point, there's going to be some fundamental rethinking about how people get to the memory subsystem and not look at it as kind of a useless commodity item on the side, but rather how does that actually become a first-class part of system design. And, and it's not just about DRAM. There are actually lots of proposals out there about very dense, non-volatile, flash, spintronics, magnetic RAM type of structures. The question is, if you're designing a system, 5 years, 10 years from now, will you have to know everything about all these different RAM technologies, or could you actually just think abstractly about the problem and choose the right one and put it behind a bus and things just work as expected? And I guess that's what we are trying to explore in this hybrid memory cube. And the solution could look a bit like this. So if you take the top picture here, we have a JEDEC link that intricately understands this DRAM based on spec sheets. And I think one of these slides says that actually the timing spec for JEDEC, just the timing bit of it is 9 pages. So it is, it is a very involved spec to actually get things to work. And what we are really looking for is some sort of an intent-based interface where the programmer and the SoC designer can just talk about memory in an abstract way. Just give me this bit, or can we even a higher level construct like a hash table, and then the details get executed by the memory controller on the other side. Now to do this, you need some bridge on the SoC, a physical way of connecting, and some thin bridge on the other side. And then you need this abstract interface that the programmer and the SoC designer can talk to. And then it's down to the DRAM or the RAM makers to actually figure out how they actually achieve the services that this higher level abstract interface promised them. And perhaps you could start moving some of the compute closer to the DRAM itself and build up some compute infrastructure on the other end much closer to the DRAM structures as well, because that's fundamentally where you end up having, you can actually do high bandwidth, efficient, low latency operations there. Not everything, but you can start with some mem copies and mem sets, and maybe that will be a good way of actually dealing with the power problem. So I will stop here now. Thank you very much, and if you have any questions, let me know.
Stefanos Kaxiras.